The second talk for today is from Alejandra Rinco Hidalgo from ICTP Trieste, and she will give a talk about Moduli of Bridgeland semistable holomorphic chains. Thank you, Alejandra. Go ahead.
First of all, thanks a lot to the organizers for the invitation. And so today I'm going to talk about Moduli of Bridgeland semistable holomorphic chains. This is a joint work with Dominique on it. And yeah, I hope it's clear enough. So first of all, I'm going to start with some motivation, because the two main components that we're going to talk about today is stability conditions and moduli spaces. So we're going to talk about the stability conditions on triangulated categories. So at least why we care about DBX. So here for us, during the whole talk, we're going to have that X is a smooth projective variety over C, and DBX is going to be the bounded derived category of the abelian category of coherent shifts. And first of all, we care about DBX because we expect to capture more of the birational geometry of X. I'll try to give some example here. And in order to study stability conditions and also part of the birational geometry of X, is going to be important to study some type of abelian categories inside DBX that actually are going to be called hards. We'll see that afterwards. So here, if we have an abelian category, we can give the space of stability conditions that was given by Bridgeland, and it's going to be a complex manifold. And it has some nice features. For example, it's going to have a well-behaved wall and chamber decomposition. And more or less what it means is that if we have a stability condition, and if the moduli space of objects in our abelian category or with some fixed data exists, we're going to have that in the stability manifold, we're going to have some chambers where the moduli doesn't change, and when we cross the wall, it's going to change. And what we expect is that this wall crossing is given by birational morphisms. So for example, Toda proof that we can recover all the minimal model program for surfaces via wall crossing of the Bridgeland moduli spaces. So that's more or less what we expect to capture. That's what I mean with respect to capture more of the birational geometry. So I hope this is some motivation. And then I'm going to start with the definition of a Bridgeland stability condition, because we're going to work mostly with Bridgeland stability conditions. T is going to be a triangulated category. We can always assume there is the bounded derived category of an abelian category. In our case, that's going to work quite well. So a stability condition is going to have two components. The first component is called a heart of a bounded structure. And what it is an abelian category inside our triangulated category, that how I like to say is that it covers our triangulated category via sheaves. So what it means it is that we have a homological functor with values in A, but I see it like a cover of T in terms of the sheaves. And the second component of a Bridgeland stability condition is a stability function. That is a group homomorphism from the Grothendieck group of A to C. The Grothendieck group of A is the free abelian group generated by the isomorphism classes of objects of A up to short exact sequences. And this group homomorphism has the property that the image is contained in the upper half plane together with the negative real line. We define the phase of every object here as the argument over pi, so it's going to be between 0 and 1. So let me try to explain why the stability function makes sense, or try to explain how I see it. So Rudakov gave a definition of a stability condition on an abelian category, and the way, really naively, the way he gave it, naively, the way I'm going to explain it, the way he gave it is that he gave a preorder on the objects of A, such that every time that you have a short exact sequence, the object in the center is always going to be in the middle. So for example, when you think about slope stability and you have a short exact sequence of vector bundles, that happens with respect to slope stability. And of course, this definition has more conditions. But the point that I want to make is that this group homomorphism makes exactly that. Since the Grothendieck group is additive with respect to short exact sequences, when you have the image in the complex number, the object in the middle is always going to be between the face of the object in the middle is always going to be between the faces of the other two. So it captures the definition of Rudakov. And moreover, here we are only working in an abelian category, and our face is going to be 0, 1. So here appears the role of the T structure, and we use it like a covering space, quotations, in the way that we're going to start gluing the information of the stability with the chiefs, and then it's more or less here in our heart we only have it from 0 to 1, and in the other objects we have it from 1 to 2 to 2 to 3, and to cover all the real numbers. That's how we're going to extend the definition from the abelian category inside T to all T. So now we can define what is going to be first, what is going to be our slope and what it means to be semi-stable. So we have our group homomorphism, and we're going to be able to define a slope, and it's going to be given minus the real part of Z over the imaginary part when possible. And this slope is going to give us the definition of semi-stable in the usual way. It means that an object is semi-stable if we have, for proper subobjects, the slope is smaller or equal. And yeah, of course, we have the relation between the slope and the face. It works well. So now we can give the definition of a stability condition. So first of all, is a heart of a bounded structure, a stability function. We have that it has to satisfy the Hart and Arasimhan filtration with respect to this slope, defined in the same way, in the usual way for slope stability. And there is also a property that I'm not going to talk much today, but it's very important, is the support property, was introduced by Conservation Seibelman. And this property will guarantee that we're going to have in the stability manifold a well-behaved wall-on-chamber decomposition. So we're going to call stab T the space of stability conditions of a triangulated category T. And here, for example, we just recover the usual slope stability in the case of curves. This is degree over rank. Usually we don't get the standard Hart is not gonna allow a stability condition, for example, in surfaces. So Bridgeland proved that the stability manifold in convenient cases, or cases in general, is going to be a finite dimensional complex manifold. We also have two groups acting on the stability manifold, the group of automorphisms of T and the universal covering of GL plus 2R. This action, we're gonna use it to more today than the other one. So now I get to talk about the category I care about. So X is, again, is a smooth projective variety over C, and the category we are working with is the category of chains, where they are a chain of morphisms and the EIs are coherent shifts over X. So it's a representation of AN quivers on the category of coherent shifts. This is an abelian category, and we care about studying the bounded derived category of this category. And this category, we're going to call it the category of holomorphic chains. So why does it is important, or it makes sense to study stability conditions here? So first of all, there is already a notion of stability on the category on the abelian category of holomorphic chains. The alpha stability is defined for chains of vector bundles. And this, you can construct nice moduli spaces via GIT. This was done by Bralo, Garcia Prada, Goten, and Alexander Schmidt. And these moduli spaces, they have been mostly used to study Higgs bundles. When you have the Hessian vibration and you have the C star action, the fixed locus, you can describe it via a holomorphic chains. So that's also why it is important. In the case when n is equal to, when is the representation of the A2 quiver, we call it holomorphic triples, and this is, we denote it like TX. So the goals during these years, they have been, first of all, to study the triangulated category, and in general is of representations of the AN quivers in abelian varieties. And the two main components that we use here always are semi-orthogonal decompositions and the existence of a functor. The second part was to describe the stability manifold, and of course is going to depend of the stability conditions that they already exist in stab of DBX. And the third one is to construct moduli of Bridgeland semistable objects and to study wall and chamber decompositions. So those are the goals so far. So today we're going to focus just on one of them, and it is we're going to discuss about this theorem that we proved with Dom, that it is for all stability conditions on the category of holomorphic triples over a curve of genus bigger or equal than 1. We proved that the moduli stack is an algebraic stack of finite type over C. And actually, it admits a proper good moduli space. I will talk about that afterwards. So we're going to focus on try to see how we can prove this. So the main tool that we're going to use are semi-orthogonal decompositions. So when we have T, a triangulated category, we have DI, they are going to be full triangulated subcategory. We are going to always assume that they are admissible. This is usually called a strong semi-orthogonal decomposition. Admissible means that the left adjoint and the right adjoint of the inclusion, they exist. And so we say that we have a semi-orthogonal decomposition of T in terms of the D1 to Dn if we don't have morphisms from in this direction. So from Di to Dj with I bigger than J, and T is the smallest triangulated subcategory containing all the D1 to Dn. So one important thing that we can always give when we have a semi-orthogonal decomposition is that we can already compute the Grothendieck group of the triangulated category. And we can always play with, we can imagine our triangulated category like split in pieces in some way. So the second and first examples of semi-orthogonal decompositions. So the easiest example is when we have an admissible subcategory. We can take the orthogonals, either the left orthogonal or the right orthogonal, and we get immediately two semi-orthogonal decompositions. And the one that we care, this is going to be the standard semi-orthogonal decomposition. This triangulated category has many more semi-orthogonal decomposition, and when describing the triangulated category and when constructing the stability conditions, they play a role. But for today, we only gonna use the standard one, and the standard one is given by D1 to Dn when they are all equivalent to dBx, and we just put Di inside Txn with E in position 9, and everything else is going to be 0. So for every simple representation of the AN quiver, we have one Di. That's more or less what we have. And in the case of we have Tx, the triples, this is going to be how we see our semi-orthogonal decomposition. And therefore, we always have, for example, the Grothendieck group and the numerical Grothendieck group of our category of holomorphic chains over curves, and is going to be always given by rank degree, rank degree, rank degree. The second tool that we're going to use is Recolmont, given by Bailison, Bernstein, and Deligny. It is that when we have a semi-orthogonal decomposition, if we have hearts, one heart in D1 and one heart in D2, we can always give a heart in T. And this heart is called the Recolmont of A1 and A2, and it's given here. We're not going to use the precise definition. And moreover, if we have an orthogonality condition, this condition, we're going to have that we actually can obtain stability conditions. So if we have stability conditions in the DI, discrete stability conditions, it means that the image of the set in C is a discrete set. We're going to be able to glue them to obtain a stability condition on T. So we have discrete stability conditions of stability I. We're going to induce a stability function that is going to depend of the set I, and it's actually given, of course, by the semi-orthogonal decomposition. And this Recolmont heart and this set is going to give us a pre-stability condition. It means a stability condition without the support property. We need to prove additionally. It's going to give us, since they are discrete, we're going to always have the Harden-Narasimhan filtration. The only thing that we need to prove additionally is the support property. So when we have the orthogonality condition, thanks for paper of Collins and Polishuk, we have gluing, and we can get these stability conditions. And also, when we have the orthogonality condition, an A1, A2 are Noetherian, the Reckel-Monhart is also Noetherian, that also plays a role afterwards. We call this type of stability conditions gluing stability conditions. Okay. So first of all, so we go back to the stability manifold of the holomorphic chains on curves. And as I mentioned before, we're going to have that the numerical Grothendieck group is going to be given by rank degree of each of the components. And the important part here is that we're going to recover alpha stability, the classical alpha stability. And the moduli space, as I said before, is given by GIT. So the heart is going to be given by a Reckel-Monhart, and set alpha is just going to be given by this. The important fact here is that we recover alpha stability, and we're going to use actually that the moduli is already constructed at some point. For in the case of triples, we describe the whole stability manifold. We prove that it is connected and is a 4-dimensional complex manifold. It is not trivial nor expected in the way that the category of holomorphic triples has homological dimension 2, and the ones that are described, the quiver ones and the one of the curve that are described completely, they are homological dimension 1. So it is nice that we can describe it all, and we can describe explicitly each stability condition there. So in this case, they are either gluing stability conditions, or they are in the orbit of a gluing stability condition. And if they are not in an orbit of a gluing stability condition, the heart is one of the ones that already appeared, either as a gluing or as in the orbit of a gluing stability condition. So this classification also plays a role afterwards to study the moduli in each of the cases. So again, I go back to our goal, that is to prove that the moduli stack is algebraic of finite type over C. So the way of doing this is, first we're going to consider Lieblich moduli space for admissible subcategories of DVX. This was first done by Lieblich in the case of DVX, and for the admissible categories was done by Bayer, Laus, Macri, Noah, Perry, and Stellari. And this is the moduli stack of perfectly gluable objects. And the important part is that the objects that we are parameterizing, or they satisfy these three conditions. We're gonna focus right now in this one. This condition that the negative x are 0 is important, because for us, every object that is in the heart of a bounded structure satisfies this condition. And the other condition is just that is in the admissible category. So what they prove is that this is an algebraic stack of locally finite type over C. So the first thing is that we need this condition to be satisfied for us. So the first step that we did was to construct geometric realizations. To construct geometric realizations, what it means is that we found explicitly a smooth projective variety YXN and a fully faithful embedding of the category of holomorphic chains inside DB YXN. Orlov did it for quivers. He constructed geometric realization for the bounded direct category of let's say AN quivers, is more general. And what we did was following more or less his steps, but instead of using exceptional collections, we use orthogonal decompositions, and we glue it at the level of DG categories. Then now that we have that TXN, it is inside a DV XN, so we can use Lieblich moduli to have our moduli problem. So our moduli problem is going to parameterize to classify all the sigma semi-stable with fixed class and fixed phase, and is going to be a substack of the stack of perfectly gluable objects. So now, in order to be able to talk about our moduli, we need to talk about families of objects, right? And base change. So first of all, we need the base change of the semi-orthogonal components. And second of all, we need the base change of the heart. So the base change of the semi-orthogonal components was given by Kuznetsov. And if we have the semi-orthogonal decomposition, when we have the product, we're going to have this semi-orthogonal decomposition. I didn't give here the definition precisely, but in our case, when we have a really nice S, the base change is exactly what we expect, that it is the chains over the product. And that's nice. And the base change of a heart is given by Abramovich and Polishuk, and is given like this. The way the intuitive way of seeing this, at least for dvx, is, for example, when you have X a projective bundle, you know you can decompose dvx in terms of a projective bundle over Y, let's say. So you can see dvx in terms of dvy's, and then you can glue the hearts in Y to get a heart in X. And that's the first step. And then you use the projectivity to extend it to more complex X. And so we have the base change of a heart. And this satisfies that it's actually a shift of the structures. And what it means is that it behaves well with respect restrictions. So we have U prime inside U, and we base change A with respect to prime. When we take the restriction, is going to be one contained into the other one. So the trivial example, if we have A, the base change of A coherent shifts over X, the base change is going to be coherent shifts of X times S. One of the first lemmas that it makes sense and is nice is that when we have a semi, and it's really general, it doesn't use the triples, is that when we have a semi-orthogonal decomposition, and we have, again, the admissibility. From now on, we're always going to use the admissibility inside a dvy. And if we have hearts inside D1 and D2, Recalmont is stable under base change. It means that the Recalmont heart that we have when we base change it is going to be the Recalmont of the hearts that we, of the base change hearts. And that plays an important role afterwards for us. So the strategy to prove that our moduli stack is algebraic of finite type, it is precisely this one. So to prove that it's algebraic, there are two properties. This is following Toda, he did it in the case of K3 surfaces, and it is a strategy given by Abramovich and Polishuk. So first of all, we have two properties, the open heart property and generic flatness. The open heart property, it is important that it is for Noetherian hearts. I'm not say what they are explicitly, I'm going to say what we can prove and in which cases. But these two conditions are going to give us this open stack, and that give us that is algebraic. And the boundedness, that is more or less the usual boundedness that you imagine, is going to give us that is a finite type over C. So heart condition requires heart to be Noetherian, and in order for us to work with Noetherian hearts, we always need to work with discrete stability. First, prove that the stacks are algebraic and phi type for all the discrete ones, and then we use the support property to extend it to the whole stability manifold. So in the case of the open heart property, we prove it in a very general way, using that the base change of the Recalmont is a Recalmont, and we constructed a heart A prime, which it is in our geometry realization that contains the heart A that we want to prove the open heart condition for. And what I want to say is this is really general. This is not only for the chains. This is more or less a strategy to prove the open heart property for admissible subcategories of a dvy. So this is this is nice in that way. The generic flatness, it really depends on where you're working. So for example, in the case of curves, it's already proof, and then we use that in the case of courses proof to prove it for gluing ones, and then under the action, and to use the classification that you saw before. So the generic flatness, it depends on where you're working. And in the case of course, everything, we're able to prove it for all oral stability conditions, because it also depends, it's a condition of the heart. So it works well with respect to our classification. And boundedness, the important part in the case of boundedness is that it is extended in connected components. So we already proved, as we mentioned, that staff TC is connected. So, and we already know that the alpha stability, the moduli is constructed via GIT, so it is going to be bounded. So we extend just by connectedness that all the discrete stability conditions, we need the discreteness, are going to be bounded. For all the discrete stability conditions, the moduli space is going to be bounded. And yes, but the important part is it can also be proved by hand. We can also prove it by hand. Why I make this point? Because now we go to our main theorem. It is that, as you know, that we were mentioning before, that it is an algebraic stack of finite type over C. Moreover, Alper, Halpern, Leister, and Heinloth, they proved that it admits good moduli. We prove that is proper. It is not hard to prove that is a proper good moduli space. So we have a proper algebraic space. We are now proving that is projective. There is like Bayer and Macri, they already constructed some Neff bundles that they're gonna work pretty well in our case, and you can prove that they are actually Neff, and then you can construct sections to prove that they are semi-ample and to prove the projectivity. Which is nice about that, it is that since the boundedness you can prove it by hand, it will give you a way to prove that the moduli space is projective without using GIT. And yeah, and that's like there is already some examples of, for example, the moduli space of curves doing everything via stacks and with moduli, and to prove that they are projective without passing via GIT. So this is also going to happen in our case. And my further remarks are that in the case of chains, this was done for triples. So in the case of chains, for the gluing stability conditions, we can prove everything. So in a connected component of the gluing stability conditions, we have that the moduli spaces are also algebraic stacks of finite type over C. In the case of, for example, K3 surfaces or some trifles, the generic flatness is also proved. So we know that generic flatness extends for gluing stability conditions. So for gluing stability conditions, we also have already the open heart property and generic flatness. We haven't proved boundedness, but it's expected to be bounded. So, and it could be done by hand. So in the case of triples or over K3 surfaces, that also we also going to obtain modularized algebraic stacks of finite type over C. So that's more or less all. And thank you. I hope it was not that fast, and I am happy if you have any questions.
Thank you very much, Alejandra. Thank you. And yes, if there are comments or questions.
I have two questions.
Go ahead.
The first one, you said it is an algebraic stack, right?
Mm-hmm.
So you mean that it is locally the quotient of a quasi-projective variety by a yes.
Yes, the Artin stacks. Okay. Yes, they will satisfy that. Yes. Mm-hmm. Yeah, exactly. Okay, algebraic or Artin. Yeah. Mm-hmm.
And you mentioned at the beginning that the steps of the minimal model program can be viewed in terms of stability conditions and this case. Does the description of this stack help in this direction, or do you think it needs to be processed further?
This minimal model program for surfaces is already done by TODA, and it works well. In our case, we expect to have the wall crossing is very well described for alpha stability. So
cool.
we would like to see if Brad alpha stability is just one of the parameters in our stability manifold. So we would like to see if there are further like more wall crossing with respect or something, if our wall crossing adds something to the picture, and that will be interesting. And yeah, but we haven't studied yet precisely the wall crossing with respect to the picture. Yes, and that's our next step now. They are projective, and now we go to study wall crossing. Yeah, and the rational geometry.
Yeah, cool, good, very nice.
Thank you.
More comments or questions? Otherwise, let's thank Alejandra again. Thank you very much.